We have explored how gold-198 delivers targeted radiation inside the human body. To understand its full engineering capacity, we have to scale up from the capillary vessels of a tumor to the heavy pipelines of global industry. Modern petrochemical refineries and mineral processing facilities operate on a massive scale, processing millions of gallons of highly reactive fluids every day. These chemical reactors are essentially black boxes. They process materials at extreme heat and immense atmospheric pressures, all safely contained behind several inches of solid steel. You cannot simply look inside. Optical cameras melt. Molecular dyes decompose instantly. Traditional flow sensors are crushed or corroded by the chemical slurry. Plant operators need to know exactly how fluid is moving inside these vessels to prevent mechanical failure, but the physical environment destroys any conventional tool sent in to measure it. The International Atomic Energy Agency relies on a specific nuclear solution, diagnostic tracers utilizing gold-198, produced via the Szilard-Chalmers reaction. The decay profile of this specific isotope allows it to transmit precise fluid dynamic data through the ultimate physical barriers of heavy industry. The diagnostic process begins by injecting a sharp, highly concentrated pulse of gold-198 directly into an industrial reactor's inlet manifold. As the isotope flows through the system, it decays. With each decay event, it emits a highly energetic gamma photon, measured at 412 kiloelectron volts. At 412 keV, these gamma photons possess the exact kinetic energy required to travel straight through high-pressure steel reactor walls without being completely absorbed by the metal. External to the reactor, engineers position arrays of thallium-doped sodium iodide scintillation detectors to capture these exiting photons. Because the detectors sit on the outside of the steel, this monitoring happens operando. The chemical plant continues running at maximum output while the internal flow is measured. In industrial chemical engineering, this macro flow mapping technique is called residence time distribution, or RTD. Harnessing highly penetrating gamma radiation effectively makes thick steel invisible to the engineers operating the plant. Capturing gamma photons through steel yields a continuous stream of raw radiation counts. To be useful, those counts must be mathematically converted into a model of fluid dynamics. Engineers apply a specific mathematical framework to this data, known as the tanks in series with backmixing model. This chart plots radiation activity on the y-axis over time on the x-axis. The smooth bell curve represents the theoretical perfect flow of fluid, while the jagged line tracks our actual empirical radiation data. Any deviation between that perfect theoretical curve and the empirical data line indicates a physical flow failure inside the reactor. A long trailing distortion at the end of the activity curve confirms the presence of stagnant dead volumes, zones where fluid is trapped and reacting longer than it should. Conversely, an early sharp spike in the radiation count reveals fluid bypassing, meaning the chemicals are channeling straight through the catalyst beds without reacting at all. These hidden flow inefficiencies waste massive amounts of raw material and drastically increase the risk of overpressurization and vessel rupture. The analytical model transforms invisible radiation data into actionable intelligence, allowing operators to preemptively shut down and repair failing reactors. Residence time distribution maps the bulk macro-level flow of the plant. However, optimizing a chemical reaction requires understanding the highly localized, chaotic microturbulence inside the fluid. To measure flow at this microscopic scale, engineers use radioactive particle tracking. Instead of a pulse of liquid tracer, radioactive particle tracking deploys one single highly active gold-198 nanoparticle into a massive churning tank. Synchronized, multi-angle detector arrays mounted outside the massive industrial tank triangulate the precise spatial coordinates of this individual point as it moves in real time. By plotting the coordinates of this single moving point over thousands of frames, the system maps a complete three-dimensional Lagrangian velocity field of the reactor's interior. This empirical data reveals the specific phase holdup profiles and turbulence intensities of the liquid. In modern engineering, these fluid dynamics are usually predicted using computational fluid dynamics, or CFD. This split-screen visualization compares theoretical CFD to physical data. CFD relies on predictive supercomputer algorithms. If the initial assumptions fed into the software are flawed, the resulting theoretical model will be cleanly mathematically wrong. The visual divergence here is severe. The simulated vector field on the left projects symmetrical efficiency, while the physical tracking data on the right proves the actual flow is completely chaotic. Engineers are required to extract the physical tracking data and feed it back into their supercomputers to continuously correct the computational math. Without the empirical ground truth provided by a radioactive isotope, theoretical physics models become a dangerous liability in critical infrastructure. Applying this technique inside a petrochemical fluid catalytic cracker introduces an extreme thermochemical variable. The internal temperatures exceed 500 degrees Celsius in a highly corrosive atmosphere. If you inject a conventional molecular radiotracer or industrial dye into this environment, it immediately melts, decomposes, or reacts with the surrounding petroleum. Material scientists solved this by designing an architecture known as gold core silica shell. The refractory silica outer layer acts as a thermal and chemical insulator, effectively decoupling the radioactive gold-198 core from the aggressive chemistry around it. This physical encapsulation ensures the nanoparticle maintains its exact morphological integrity, even when subjected to high neutron fluences and extreme heat. By using advanced nanoengineering as a physical shield, the nuclear tracer survives an environment that destroys almost every other synthetic material. The utility of gold-198 extends beyond the closed loops of industrial reactors. It is also deployed in massive, open environmental systems. Engineers directly label fine silts with gold-198 and release them into open coastal estuaries. The objective is to trace sediment flow to accurately map harbor siltation, tidal transport patterns, and the dispersion of industrial discharge. Intentionally introducing a highly radioactive isotope into a vulnerable coastal ecosystem presents an obvious environmental concern. This chart illustrates how the 2.7-day half-life of gold-198 perfectly aligns with the required timeline of tidal macro transport cycles. Within a few weeks, the radioactivity curve drops completely to zero. The gold-198 entirely decays into stable, inert mercury-198. This precise temporal resonance allows environmental engineers to extract high-resolution flow data during the study period, while guaranteeing zero long-term radiological footprint in the ocean. The journey of this isotope begins with neutron capture inside a nuclear reactor, triggering localized Auger dose enhancements to synthesize a nanoscale tracer. The same decay profile that allows oncologists to deliver targeted nanobrachytherapy allows chemical engineers to penetrate steel and environmental scientists to map the tides. Harnessing the physical decay of gold-198 provides the empirical data necessary to optimize global manufacturing and protect open coastlines. When standard observational tools fail, looking to the exact, predictable mechanics of nuclear decay offers a way to measure the invisible.